one really big question that you often face in real life in chemistry is, how do you know what you've got? So if you've made something by a reaction, or if you've purified something out from nature or whatever, the question is, how do you know what you've got? And there are really two aspects to that. One is, if you've got a pure substance, working out what its structure is, and you've already learnt a little bit about that in terms of having learned about mass spectrometry and infrared, and we'll learn about more spectroscopic methods that help you with that identification process later this year. But there is another thing, which is that in general you want to know, have I got a mixture or have I got a compound? And if I've got a mixture, how many components are in it, and ideally what are they? And that generally requires a technique where you can separate out the components of a mixture. And the sort of preeminent technique that chemists tend to use for separating mixtures out, both on an analytical scale but also sometimes on a preparative scale, but at A level we're concerned with it mainly as an analytical method, is chromatography. So let's have a look first of all at what we mean by that word. What you can see here is a brown spot. It's just an everyday brown spot of the sort that you might meet any day in the street. And what we're going to do is look at what happens if we gradually apply a solvent to the centre of the spot. So let's just do that. So if we just carefully add a drop, and you can see straight away that the solvent is spreading out, and as it does so, the spot starts to spread out as well. So if we keep adding some more, we can see that the spot is getting bigger, or at least the solvent is spreading out. But something very interesting is happening as well, which is that instead of the colour of the spot spreading evenly out, it's actually separating. So you can see by this point that we've got quite clear separation into, we'd have to say, at least 3 components. So we've got pink in the middle, which has hardly moved at all from its starting point. We've got this sort of yellowish green band which has moved quite fast but hasn't quite kept up with the edge of where the solvent has got to. And then we've got this reddish brown component round the outside which has moved fastest of all and basically is more or less at the same position that the solvent itself has got to. So what this demonstrates in a very crude way is chromatography. That you can separate substances out based on their mobility when you have a solvent and when you have what we call a stationary phase, which in this case is my old gardening shirt, but as we'll see that's not what you normally use in chemistry, but its role is to slow down the movement by opposing the ability of the mobile phase, which in this case is the solvent, to drag the substances with it. So what we need to do is to understand what's going on in terms of this competition between the solvent and the shirt. In more technical language, between the stationary phase, in more technical language, between the mobile phase, which is the solvent, and the stationary phase, which is the shirt. So let's just really go through what exactly is happening in this experiment. So here's our starting point. So we've got our focus spot in the middle there, and we apply a little bit of solvent to it, and the point is that the solvent then starts to spread out in all directions. And as it does so, it gives the opportunity to any of the substances in that spot to dissolve and therefore get carried with the solvent as it goes. So if all these substances just dissolved readily in the solvent and sort of waved the shirt material a cheery goodbye, they would just travel with the solvent as it migrated, and what you would get would be a sort of ring of this brown material getting ever bigger as the solvent expands. And that would be obviously of no use to us then as an analytical method. But what happens in reality is that there's a competition, because the material that the shirt is made out of, remember, has adsorbed the materials in the spot at the beginning. That's why it's stuck on the surface. So there are some kind of intermolecular forces between the shirt and these adsorbed substances. When the solvent comes along, it's offering an alternative set of intermolecular forces between the solvent molecules and these molecules that we're analysing. So what we have is a competition. The shirt, which is our stationary phase, is competing with our solvent, which is the mobile phase, and they're both offering the substances in the sample a set of intermolecular forces. And basically it just depends on which set of intermolecular forces suits an individual substance better as to whether it will tend to remain stuck to the shirt because it can form stronger intermolecular forces there, or whether it will tend to go into solution because it will interact better with the solvent. And that will be different for different substances. So what actually happened, remember, was that we got essentially 3 rings. So we got one out here, which was the sort of outer reddish brown ring, and that was more or less keeping pace with the solvent. So what we can conclude there is that those molecules interacted much more favourably with the solvent than they did with the stationary phase, okay, because they were just lifted cleanly off here and carried with the solvent as it went. Now just inside that we got this sort of greenish yellow layer, and it obviously wasn't nearly as cleanly separated as that, but it was just lagging a bit behind, as we saw. And so what's going on there is that this time it's not such a one-sided competition, that these molecules are dissolving, they are being carried outwards by the solvent, but they're not completely ignoring the shirt. They're being slowed down by it, because every so often a molecule will be stopped and will reabsorb to the shirt and then get on its way again. And that limited tendency to remain adsorbed slows it down. So it still migrates, but it migrates slower because of the competition with the shirt molecules. So comparing the green substance with the brown one, we could either sort of view it from the point of view of the solvent and say, well, the brown one seems to be more soluble in the solvent than the green one, or we could view it from the point of view of adsorption and say, well, the green one seems to adsorb more strongly to the shirt material than the brown one does. And in reality, it's kind of a balance of those two things. But for A-level purposes, we focus on the adsorption generally. That's accepted as the sort of straightforward way to explain these things. So what we would tend to go with is to say that the green substance migrates more slowly because it's adsorbed more strongly to the stationary phase than the brown one is. What we also had was a pink spot which seemed hardly to move at all. And so in that case, what we would conclude is that it's adsorbing very strongly, so the solvent basically just can't compete with it, and so it remains stuck to the shirt. So substances which move very little, that's because they're adsorbing very strongly to the stationary phase. So what we need to do now is to take these ideas from this very simple experiment and see how they lend themselves to a much more precise kind of chromatography, which you can apply to analyse mixtures from organic reactions.